Welcome everyone to our discussion today, and we're honored to have Jeff Groah from math. Thank you, Jeff, for taking the time to put all this together. And this is based on a paper that Jeff wrote, and his topic is Wandering Through Space and Time, Mercury.
And we'll do this through both space and time, as you'll find out. We're going to begin by talking about Urbain Le Verrier, who in 1846 discovered Neptune by pencil and paper. See, people had been studying Uranus for some time, astronomically, and knew that Uranus was not traveling in the orbit that was prescribed by Newton's theory of gravity. There were some deviations and being pulled that away somehow. And so Le Verrier sat down with pencil and paper based upon the observations that had been made and said, well, there must then be a planet here. And so he sent this note to the Royal Astronomy in France, and within 1 degree, they found Neptune. It was a pretty remarkable achievement. So he discovered it by pencil and paper, and in fact had the other astronomers then find this thing. He was actually appointed ultimately to be leader of the astronomy there in Paris, but he was known to be an SOB, such that it was very difficult for people working under him. He made things so that they didn't function very well. And he was removed from his position because he behaved so badly. He was later placed back into the position after the person who succeeded him, I think, passed away, but he was placed back into that position with restrictions on what he could do. So he couldn't be the SOB that he was born to be, I guess. But nonetheless, in 1859, he discovered that something was amiss with Mercury. Something wrong with Mercury, something about Mercury. Mercury wasn't where it was supposed to be. It was wandering through the solar system on a path not prescribed by Newton's theory of gravity. And he checked a number of different things, as you'll see.
Jeff, would you like the lights down?
Oh, it might help if the lights were dim so you can see the PowerPoint. According to Kepler, planets move about the sun in the shape of an ellipse with the sun at one of the foci. The sun is at one focus. And they move faster when they're closer to the sun and slower when they're farther from the sun. So this is what Kepler deduced from the observations that he stole from people. And this conclusion is confirmed by Newton's theory of gravity. Newton's theory of gravity implies Kepler's laws. So the planets are supposed to be going in these nice ellipses with the sun that will focus. But what's happening with Mercury is that the ellipse is precessing like this. So it isn't moving in a nice ellipse. So what is actually going on? The perihelion of a planet is the point in its orbit where it's closest to the sun. That's called the perihelion. For objects in orbit around the Earth, it's called the perigee. I guess for every planet in the solar system, they have another name for this, but for the sun, it's the perihelion. And what's happening is that Mercury's perihelion is precessing forward like this. So its perihelion is advancing by some amount. However, as depicted here, this is a huge exaggeration. Come on in. It's an absolutely enormous exaggeration. So let me try to describe what sort of exaggeration we're talking about. I've tried to graph what 1 degree looks like here.
That's the best the maple can do, huh?
Yeah, for 1 degree. Now each degree of angle is divided into 60 minutes. If I were to shoot a rifle at rifle range at 100 yards and adjust my aim by 1 degree, I would miss by 5 feet. Okay? So at 100 yards, 1 degree of angle corresponds to 5 feet at the end of the range. Which means that if you're only accurate to within 1 degree on the rifle range, you're not going to hit the target at all. Okay. because the target is, what, a couple feet, a foot and a half or so. So that would be bad. However, on a rifle range, since each degree is divided into 60 minutes, each minute of angle here on a rifle range at 100 feet, 1 minute of angle corresponds to 1 inch. Okay. So if you miss by 1 minute of angle, that's 1 inch off at the end of the rifle range. Well, each minute of angle is divided into 60 seconds of angle. Okay, now you can imagine. Mercury's perihelion advances about 1/10 of an arc-second per orbit. When did Leverrier discover this? 1846. 1846. The astronomical observations in 1846 were so precise that this was way beyond the errors and revisions. They had this down. This on a rifle range at 100 yards, 1 second of angle corresponds to 2/1000ths of an inch. Okay, or the 1/10 of an arc second corresponds to 2/1000ths of an inch. 2/1000ths of an inch. So you're missing by a hair's breadth if you're missing by a second of arc at 100 yards on a rifle range. That's way more accurate than I can shoot at a rifle range. I get a 4-inch spread usually, 2 inches this way, 2 inches that way, if I'm shooting at 100 yards in the rifle range. That's not bad, I am. So I'm maybe two minutes off, 2 arc minutes off. That's how accurately I can shoot a rifle at 100 yards. This would be 2/1000ths of an inch, this small variation. However, as a result of that 2/1000ths of an inch, with each orbit, Mercury passes by the Sun 0.6 seconds earlier than expected with each orbit. 0.6 of a second earlier, which is kind of remarkable because Mercury orbits the Sun 4 times a year, so that's 2.4 seconds, and over a course of 10 years, that would be 24 seconds. That's certainly measurable over a course of time. Okay, so it builds up with all these different orbits. There's Mercury transiting the Sun. And so this is something you can observe, right? You can observe Mercury transiting in front of the Sun. You can time it, you can figure out when you can have it. One of the known sources of perturbation in Mercury's orbit, I've lied to you. I said this was a small perturbation. Have I told you how much this perturbation is? I haven't told you. Okay, so the perturbation that is due to these other planets in the solar system, including Venus and the Earth, Mars and Jupiter and so on, Leverrier accounted for that. They are pulling Mercury's orbit out of whack a little bit, and Leverrier accounted for this. Large computations, you can imagine the computations in 1846 that were necessary to account for that. Well, he did, and he came up with 526.7 arc seconds per Julian century. Arcs, that's measured in arc seconds, right?
Yeah.
Whereas, you know, ASC, arc seconds per Julian century. We'll talk about Julian centuries in a minute. However, the observed was 569.7 arc seconds per Julian century, leaving 43 arc seconds per century. That was unaccounted for. Okay, so he could account for everything but the 43 arc seconds per Julian century, but that was within the error bounds. Every 100 years, 100 Earth years, Julian Earth years, the Earth would advance, the Mercury would advance its perihelion by 43 arc seconds. That's after hundreds of orbits.
Closer to the Sun.
No. The point where it is closest to the Sun marches around a little bit.
Oh, okay.
So the ellipse is advancing like that around, but very, very small amount, by 43 arc seconds per Julian century, which is pretty incredible. So it's, you know, Mercury versus all of them, and those do have an effect. It's a small effect. It's this much per Julian century in arc seconds.
So you take a measurement, you wait a Julian century, and then you measure it again, And you go, lo and behold, there's 43 arc seconds difference.
Real. Not exact. However, what is a century? 100 years. Do you know what a year is? What is a year? You say 365 days?
This year,
Point what?
366.
365.25 days.
Well, that's a Julian year,
Right.
because every fourth year you have a leap day, right? But if you look at the Gregorian calendar, every 100 years you do not have that leap day, except on hundreds that are divisible by 4, right? Okay. And so, that would give you what, 365.25, 2425?
Yeah.
Yeah.
Okay, but you could even be more accurate than that, I'm sure, because that's only what, 7 digits of accuracy?
Right.
7 digits? I need more than 7-digit accuracy to get these computations right. That's not enough, believe it or not. And so how you talk about a century matters in terms of how accurate you're going to be in these calculations. That's kind of amazing, I think, that what you call a century matters. The Julian century, we have that down, 365.25 days in a year, multiply that by 100, that is number of days in a Julian century, and each day is a certain number of seconds, according to the Julian calendar. So that can be known, that is known exactly. We know exactly what a Julian century is. We don't know exactly what, well, I guess we can calculate exactly what a Gregorian century is, but what does it mean for the Earth to go around the sun? Well, do we mean the time where the seasons, we go from shortest day to shortest day? Is that what a year is? The time from shortest day to shortest day? Or is it the time where we have the background stars here, and when we return to the spot where the background star is in the same position, that's called a sidereal year. And that's different from when you have shortest day to shortest day because of the fact that the Earth, on its tilted axis, is wobbling. Its axis is precessing. So, what is a century? Turns out these are important questions to answer if you want to get as much accuracy as you need to analyze the advance of Mercury's period. There are other definitions for a year and for a century, and we can go on and on talking about that. The Julian century we know exactly, so we may as well use that since there's no computational error in reporting those values. So, because of this unexplained advance in Mercury's perihelion, Leverrier hypothesized the existence of another planet. You see, he was successful in 1846 in predicting the existence of Neptune. But in 1859, here he is saying, there must be something else close to the sun that's pulling Mercury off that accounts for this 43 arc seconds per Julian century. It may be more than one thing, who knows? There could be an asteroid belt we haven't discovered because it's so close to the sun and you have to look right at the sun to see it. Okay. But in fact, there were reports coming in of finding the planet Vulcan. You see why Leverrier fell in love with this Vulcan? It's just like Neptune, except it's really close to the sun, and so it must be really hot. So we'll call it Vulcan, right? And that once you have assigned a name to it, it must exist, right? So, careful searches over the next 57 years found nothing. No, it's nothing. No asteroids. Planet Vulcan. Do you ever wonder where that planet Vulcan came from? Came from this search. To explain this 43 arc seconds per Julian century that Leverrier stumbled into. So, the wanderings of Mercury were an open problem for 57 years. Until Albert Einstein came in. And in 1916, he published his general theory of relativity. He submitted this in December of 1915, published I think in January of 1916, and his general theory of relativity, his first paper describing his theory of gravitation, general theory of relativity. this very paper